Hi all, I wanted to record the solutions to the practice problems from section 11.8. And so we have two practice problems that we're working on here. And keep in mind that the instructions in section 11.8 is to find the radius and the interval of convergence. So we do that by taking the ratio test. So this is the limit as n goes to infinity of the square root of n plus 1 x to the n plus 1 over the square root of n x to the n. What I'm going to do here to make this easier to work with is I'm going to put both n's under the same square root, so n plus 1 over n. And then I'm going to pull an x away from the x to the n, and that'll allow me to cancel and simplify. So I can cancel the x to the n's, and this just leaves me with, let's see, the limit as n goes to infinity of the square root of n plus 1 over n times x. And if we take that limit, the limit underneath the square root is 1, and then the square root of 1 is just 1. So this is just the absolute value of x. And I want that to converge, so I want it to be less than 1. And so right away that tells me that my radius of convergence is 1, right? And that's because I have the absolute value of x, which is where my series is centered, and then this is the value for r, okay? So then my interval is going to be from, if you think about the inequality here, this is going to go from -1 less than x less than 1. And so what we need to do is we need to check the endpoints at -1 and 1 to determine whether we should have or equal to there to determine our interval of convergence. So first, let's let x equal to 1. And if I let x equal to 1, this is a series n equals 1 to infinity, square root of n times 1 to the n, which is just the series n equals 1 to infinity of the square root of n. And if you take the limit as n goes to infinity of square root of n, that's not 0. So this diverges by the test for divergence. And then if we have x equals -1, we're plugging the -1 in for the x in the original series. So you have the square root of n times -1 to the n. And again, here, if you take a look at the limit as n goes to infinity of the square root of n, this does not equal 0, and so again, it diverges by the test for divergence. And so what that means is that we don't include either our -1 or our +1. So our interval of convergence here goes from -1, not including -1, to 1, not including 1. And so that is my radius and interval of convergence for number 1. Next, let's take a look at number 2. Now, keep in mind before we get started here that typically our power series are supposed to be x minus a to the n. And this one's got a number in front of the x. So what we want to do here is we want to kind of simplify this before we get started. So if I can rewrite this as n, and by the way, these are supposed to start at 0. Sorry about that. Let's make it 1 over n times 3x minus 2 all over 3 to the n. So both things that have an n, let's put them together. And the 1 over n is what's left. And then if you divide that through, you get x minus 2/3 to the n, and then I'll put my n back underneath. And now you can see that this is the power series centered at x equals 2/3, and you've got the 1 over n there as well. So now we can test it using our ratio test. So if we take the limit as n goes to infinity of x minus 2/3 to the n plus 1 over n plus 1, and I'm going to right away flip it upside down. So I'm going to have the original upside down, n times x minus 2/3 to the n. And I'm going to do two things here. I'm going to rearrange so that my n's are together, and I'm going to pull out one of the x minus 2/3. So I'm going to put the n over the n plus 1, and I'm going to make this x minus 2/3 times x minus 2/3 to the n. And then I'll be allowed to cancel my x minus 2/3 to the n. And I can also look at this and say, look at the limit of n over n plus 1. That's going to be just 1. So this is going to leave me with just x minus 2/3. And again, I want that to converge, so I want to make it less than 1. And so now you can see that we're centered at 2/3 and that our r value is 1. So my r, my radius of convergence, is going to be 1. Now my interval if I set this up, -1 less than x minus 2/3 is less than 1, and I add 2/3 to all three pieces, that's going to give me, over here this is 5/3, 1 plus 2/3 is 5/3. I'll have just the x in the middle. Oops, sorry guys. And -1 plus 2/3 is -1/3. Okay, and so now these are my boundaries, and now I've got to determine whether those converge or not. So I'm going to go back to the drawing board, to the original equation, and I'm going to plug in -1/3 and 5/3 in for the x. So I'm plugging in here. Okay, so let's look at x equals -1/3. And you can either plug in there, or you could plug in down here. It doesn't matter to me which one. I'm going to go with the original. So that means that we've got sum n equals 0 to infinity. You're plugging in -1/3 into that x. So 3 times -1/3 is -1. -1 minus 2 is -3 to the n. So we get a -3 to the n on top, and you have n 3 to the n on the bottom. In order to simplify this, I'm going to separate that top to -1 to the n times 3 to the n, so I can cancel the 3 to the n's. And that means I'm really working with a simplified series of -1 to the n over n. This is alternating harmonic. If you check the alternating series test, this one converges. So we're going to include the -1/3. But for 5/3, when I plug in 5/3 into that x up above, 5/3 times 3 is 5. 5 minus 2 is 3. So we get 3 to the n over n 3 to the n. My 3 to the n's will cancel out, and I'm left with the series n equals 0 to infinity of 1 over n, which we know is harmonic and diverges. So that means for my interval of convergence back up here, I am going to include the -1/3. So I want to include the -1/3, so I use brackets, and I'm going to not include the 5/3 because it doesn't converge there. And that will give me my radius and interval of convergence.